In this module, we will discuss number of tangents from a point on a circle. As we already know now that from any point on a circle, there can be one and only one tangent. Now let us know about the number of tangents from a point inside a circle. So let us draw a circle on a paper and take a point P inside it. Can we draw a tangent to the circle through this point? Let us see. We observe that all the lines through this point intersect the circle in 2 points. So it is not possible to draw any tangent to a circle through a point inside it. Next, take a point P on the circle and draw tangents through this point. We have already observed that there is only one tangent to the circle at such a point. Now we are left with only one condition. Let us see that also. Now we will take a point outside the circle and try to draw tangents to the circle from this point. Observe the figure. We can observe that we can draw exactly 2 tangents to the circle through a point outside the circle. Here, T1 and T2 are the points of contact of the tangents PT1 and PT2 respectively. The length of the segment of the tangent from the external point P and the point of contact with the circle is called the length of the tangent from the point P to the circle. PT1 and PT2 are the lengths of the tangents from P to the circle. The lengths PT1 and PT2 have a common property. Let us see in this theorem. Theorem. The lengths of tangents drawn from an external point to the circle are equal. We are given a circle with a center O, a point P lying outside the circle, and 2 tangents PQ, PR on the circle from P. We have to prove that PQ is equal to PR. Let us start the proof. For this, we join OP, OQ and OR. Then, angle OQP and angle ORP are right angles because these are angles between the radii and tangents. Now, in right triangles OQP and ORP, OQ is equal to OR, radii of the same circle, OP is equal to OP, common. Therefore, triangle OQP is congruent to triangle ORP by RHS. This gives PQ is equal to PR by CPCT. Also note that angle OPQ is equal to angle OPR by CPCT. Therefore, we can conclude that OP is the angle bisector of angle QPR. That is, the center lies on the bisector of the angle between the 2 tangents. We will do some examples now. Let us take an example. Prove that in 2 concentric circles, the chord of the larger circle, which touches the smaller circle, is bisected at the point of contact. Solution. We are given two concentric circles C1 and C2 with center O and a chord AB of the larger circle C1 which touches the smaller circle C2 at the point P. We need to prove that AP is equal to BP. Let us join OP. Then AB is the tangent to C2 at P and OP is its radius. Therefore, OP is perpendicular to AB. Now AB is a chord of the circle C1 and OP is perpendicular to AB. Therefore, OP is the bisector of chord AB as the perpendicular from the center bisects the chord, that is, AP is equal to BP. Next example is two tangents TP and TQ are drawn to a circle with center O from an external point T. Prove that angle PTQ is equal to twice angle OPQ. Solution. We are given a circle with center O, an external point T, and two tangents TP and TQ to the circle, where P, Q are the points of contact. We need to prove that angle PTQ is equal to twice angle OPQ. Let angle PTQ is equal to phi. Now, TP is equal to TQ as the lengths of tangents drawn from an external point to a circle are equal. So TPQ is an isosceles triangle. Therefore, angle TPQ is equal to angle TQP is equal to half into 180 degrees minus phi is equal to 90 degrees minus half phi. Also, angle OPT is equal to 90 degrees by the statement that the tangent at any point of a circle is perpendicular to the radius through the point of contact. So, angle OPQ is equal to angle OPT minus angle TPQ is equal to 90 degrees minus 90 degrees minus half phi is equal to half phi is equal to half angle PTQ. This gives angle PTQ is equal to twice angle OPQ.